Hello everyone. In the previous class we have discussed about the solar cell, its advantages, disadvantages and applications. A small part in that was left out. There is VI characteristics of an illuminated solar cell. So that we'll discuss first. So as you can see from the figure, so this figure shows the VI characteristics of an illuminated solar cell. So here the figure, as per the figure, the maximum power is rectangle shaded. The shaded part, whatever it shows in the figure, that is the maximum power delivered. So this figure shows the fourth quadrant portion of a solar cell characteristics. So remember here it is a fourth quadrant, but just for the sake of convenience, the IR is plotted in the upward direction. So actually it is in the downward direction, just for the sake of convenience to observe. So this characteristic is plotted upward. So this figure is a fourth quadrant portion of a solar cell characteristics. The open circuit voltage VOC, can observe the figure. The VOC is nothing but it is a open circuit voltage. The open circuit voltage VOC and the short circuit current ISC are determined for a given light level by the cell properties. Here the maximum power delivered to a load by this solar cell occurs whenever the product V into IR is maximum. So these are the values of voltage and current, that is nothing but Vm and Im. So as we can see from the figure that the maximum delivered power is indicated by the shaded rectangle in the figure. So this part, that is maximum power delivered, is less than the product ISC and VOC. So as you can see clearly from the figure, so the ISC VOC product is maximum, whereas the shaded part is less than that one. That's why the maximum delivered power is less than the product of ISC and VOC. Here the ratio, that is Vm into Im divided by ISC into VOC, is called the fill factor. The fill factor is nothing but is defined as the ratio of Im Vm by ISC into VOC. So it is a figure of merit for the solar cell design. So this fill factor is a figure of merit for a solar cell design. So already we have discussed advantages, disadvantages and applications. Now let's discuss the photodetector. Photodetectors are nothing but they are semiconductor devices. So they are going to be used to detect the presence of the photons in the semiconductor. So photodetectors are semiconductor devices which can be implicated to detect the photon presence. So they are also similar to the previous topic whatever we have discussed, that is they transform optical signal or the light signal into the electrical signal, or light energy into electrical energy. So they are going to be used for converting the light energy or optical energy into the electrical signal. So these photodetector principle is based on two types. So that is two types of a photoelectric effect. So they are nothing but, first one is the external photoelectric effect and the second one is the internal photoelectric effect. So the external photoelectric effect is the in which the electron becomes free from the metal surface by energy absorption obtained by streams of incident photons. So photo multiplier tube, vacuum photodiode are the implications of the external photoelectric effect. So this is about external photoelectric effect. The second one is the internal photoelectric effect. So here free charge carriers are going to be generated by absorption of incident photons in the semiconductor junction detectors. So here the free carriers are going to be generated by the absorption of the incident photons in a semiconductor junction detectors. The PIN photodiode, PIN, that is P type intrinsic, then N type. PIN photodiode, PN junction photodiode and avalanche photodiode are examples of the internal photoelectric effect. Here there are few important detector properties that we can list. That is, we can say the features of the photodetectors. They are nothing but the responsivity, spectral response and response time. Here the responsivity is nothing but the output current divided by the total light power falling upon the photodetector is nothing but the responsivity. Then the spectral response is the response of a photodetector as a function of photon frequency. And the last one is the response time. Response time is the time needed for the photodetector to go from 10% to 90% of the final output. So there are many properties are there, but out of this, these are the important properties: responsivity, spectral response and response time. So this figure shows the schematic representation of a PIN photodetector. So as you can observe from the figure, PIN is nothing but P stands for the P type semiconductor, I is the intrinsic semiconductor and N is the N type semiconductor. So intrinsic semiconductor is sandwiched between the P and N. Again here this arrangement is done in a reverse biased condition. So P type is connected to the negative of the battery and N type is connected to the positive of the battery. So it is a reverse biased condition. In most optical detection applications, the detector's speed of response or bandwidth is very critical. The carrier diffusion step in this process is very time consuming and therefore it should be eliminated if it is possible. So the carrier diffusion step in this process is very time consuming, therefore it should be eliminated. Therefore it is desirable that the width of the depletion region W, so width of the depletion region W should be very large enough so that most of the photons are absorbed within W, that is depletion region, rather than in the neutral P and N regions. So as you can see from the figure PIN, so these width of the depletion region W must be very large enough so that the photons, they are going to be observed within the W rather than absorbing within the neutral P and N regions. but the disadvantage is large W leads very sensitive device with a low RC time constant, and if drift time is excessive, which again leads to low speed. So we have to compromise between these two, that is trade-off. So the appropriate width for the W is chosen as a compromise between the sensitivity and speed of response. So one way of controlling the width of the depression region is to build a pin photodetector. So as shown in figure, here the eye region, it need not to be a truly intrinsic as long as the resistivity is high. When the device is reverse biased, the applied voltage appears almost entirely across the eye region. So remember here, when the device is reverse biased, that is photodetector is reverse biased, or the pin photodiode is reverse biased, the applied voltage appears almost entirely across the eye region, that is the middle region, eye region. If the carrier lifetime within the P region is long as compared with the drift time, most of the photo generated carriers will be collected by the N and P regions. So the figure of merit for a photodetector is nothing but the external quantum efficiency NQ. So here that quantum efficiency is nothing but the number of carriers, that is either it can be electrons or holes, the number of carriers generated per photon. So NQ, the NQ is defined as the number of carriers that are collected for every photon impinging on the detector, or you can also define it as the number of carriers generated per photon. So for a photocurrent density, that is JOP, photocurrent density is denoted as JOP. We collect JOP by Q, carriers per unit area per second. For incident optical power density of POP, that is the incident optical power density of POP, the number of photons shining on the detector per unit area per second is POP by h nu. Therefore, that NQ is equal to JOP divided by Q whole divided by POP divided by h nu. That is, NQ is the external quantum efficiency, which is nothing but the number of electrons or holes generated per photon. For photodiode that has no current gain, the maximum NQ is unity. So the photodiode which has no current gain, so the maximum NQ, that is the external quantum efficiency, is nothing but it is a unity, it is equal to 1. If low level optical signals are to be detected, it is desirable to operate the photodiode in the avalanche region of its characteristics. So remember here, if you want to detect a low level optical signals, then it is required to operate the photodiode in the avalanche region of its characteristics. So here each photo generated carriers cause a huge change in the current. So this leads to efficiencies greater than 100%. Thank you for watching the video.